welcome to this lecture as part of week 4, where we focus on making machine learning model developments happen in a iteratively agile fashion with the need for CI/CD, which was discussed in the previous video. Just to recap, uh, the best practices with respect to CI/CD when it comes to machine learning projects is to have your uh, code or model both in some cases be checked into a central code repository system like GitHub, and then have every single one of those check-ins, so to speak, be responsible for triggering what's called as a GitHub action. The GitHub action becomes the mechanism through which we then start to automate a lot of the continuous integration aspects of machine learning projects, which includes things like testing, running unit tests, regression tests, validating the model itself. And once the uh, approval or the sign off is provided, then that model is deployed onto the cloud platform, or the platform where the model is going to get run. And once it's deployed there, then you start to detect for continuous drifts, or you have basically continuous monitoring processes in play. So we also quickly summarized CI/CD's benefits as one of being consistent, reliable, scalable deployment delivery models. That's one of the main benefits. It automates testing, monitoring, as well as the retraining that's required whenever the data shifts away from what the model's initial assumptions are. And then it also helps the model stay up to date with provable governance. And most importantly, I think the philosophy with which machine learning engineers or data scientists have to approach machine learning in production is that ML is not a done once kind of an exercise. It is actually something that's iterative. So you've got to keep doing improvements, and therefore the CI/CD practices are a must. So with that said, in this video, we will dive deeper into what it means to use something like Git for keeping track of your code. For some of you, this might be repetitive because you've already done the programming course earlier. Some of you might have used Git actively as part of your regular job. You might still learn a thing or two as part of the primer that we will provide. Towards the second part of the video, we will look at specifically the GitHub Actions mechanism that we will leverage extensively for doing CI on our ML projects. And as part of the next video, we will assemble all together all the different tools, mechanisms that we have explored so far on both code versioning as well as data versioning, and make one end-to-end exercise happen in reality. So let's go through a quick Git 101, but instead of focusing on the typical programmer experience of how Git is used, my focus for this video is going to be on data scientists and machine learning engineers specifically. The nuance is small, but not insignificant. So what is Git? First and foremost, it's a version control system that actually helps you track changes to every single file that's part and parcel of what's called as a code repository. A code repository comprises of various aspects of what typically constitutes a software project, which is including, of course, the code itself, be it in any language, but also the configuration files like YAML files, compilation files like make files, as well as testing files. And in machine learning projects specifically, it can include weights, it can include the model itself, it can include parameters to the model, it can include even what's called as secrets, which are not to be typically discussed or displayed in the open for everybody to see, but at times these are encrypted so that it's available for the machine learning project to use in a way that's uh, decrypted programmatically. So a variety of different artifacts exist as part of a code repository. Um, Git helps you manage all of that. Why did Git become famous? I think first and foremost, it became famous because it was created by somebody who was really famous, uh, Linus Torvalds, back in 2005. And his motivation for creating it, he's articulated this in multiple forums before, but fundamentally it was stemming from his desire to provide a much more easy and flexible version control system compared to state of the art back in the day, especially for managing open source projects. And for those who don't know, Linus Torvalds also happens to be the creator of Linux, the operating system. So when he announced the use of Git for the release of some of the Linux versions back in the day, people were really blown away by the simplicity of how Git manages it, and also the ability for uh, Git to do things which are very powerful, especially for large scale collaboration on open source projects, which is typically the case because these are public projects with collaborators coming from all over the place. Most collaboration happens asynchronously, etc., etc. So uh, Git became popular as a result of usage across various open source projects. And of course, since then, what has happened is platforms such as GitHub or GitLab or Bitbucket from Atlassian, all of these became um, software code repository platforms which use the Git protocol. So the way these platforms differ from Git itself is that the Git is the protocol or the tool which defines how various aspects of code management actually happen. And then these platforms implement the protocol apart from the storage of the code and a whole bunch of other platform related features related to things around CI or CD or testing, etc. So we will actually use GitHub as part of the uh, this course. So you're welcome to use any other Git based platform like GitLab or Bitbucket. It would apply equally as well to that as well. Yeah. So the common jargon, let's make sure we all have the same understanding for this. A repo, or in short, a repo is basically denoting a repository. It stores documents and codes over time. I forgot to mention about documents. In many cases, documentation is also a part of the repo. A branch is a line of code which is separate from the main branch. So whenever a repo is created for the first time, there is something called as a master branch or the main branch. And then from that main branch, at times developers create their own branches. And that branching exercise is something that we will discuss what the best practices are, etc., a little later. Once a specific set of changes are ready to be committed um, to a particular branch, that constitutes a commit. So you can think of it as a point in time snapshot of a branch corresponding to a specific version. Usually, every commit is associated with what's called as a commit ID, which identifies that commit, and that becomes basically the version for that particular set of changes. Um, and then once a particular branch is ready to be merged into another branch, then you would do what's called as a pull request. So we will take detailed scenarios of this later on, but the typical scenario here would be there is a main branch or the master branch, which basically tracks the machine learning project for all the ways in which it's contributed to production its models. And then there is the development branch, which is separate. And the development branch, as you can imagine, keeps seeing newer and newer development for newer algorithms or newer code, newer data sets, etc. So as and when a specific level of development is done and the ML engineer decides that yes, this is worthy of putting into production, at that point, the uh, set of commits which are associated with that development branch is identified as being part of the commits that need to be there in the main. And at that time, the developer issues a pull request to the main branch. Usually, what happens is the main branch has a separate owner. Usually, it's some kind of an IT uh, in charge of what goes into production, and then they would then review this pull request and then decide whether I'm going to merge as a result of the pull request or I'm going to decline. And there are various ways of, various reasons for which you might decline. But when you choose to merge, then you issue the merge command, and then that combines the actual branch code at the code level itself. So this is the common jargon. there's one more set of principles that you'll need to understand. It's more to do with the architecture of Git itself. So Git was engineered for allowing large-scale asynchronous development on the same code base. So it gave primacy to the local development of code so that people distributed across different parts of the world contributing to, let's say, an open source project need not keep in sync, need not communicate all the time in order for getting their changes done to the code. Prior to Git, the earlier versions, like let's say for instance Subversion as an example, or even prior to that, CVS was one of the oldest and very popular code repository systems. They had significant challenges with respect to handling what's called as conflicts. Conflicts happen when a set of change happens to the same code but is being done by two different people sitting in two different places, and they go through a bunch of these changes locally, and then when they are ready to commit to the main branch, that's when the conflicts get detected, right? Because these sets of changes are not compatible. And then when such a conflict gets detected, then the main branch will throw out an error saying, I can't resolve these conflicts. And then the developers now have to sit and talk to each other, figure out whether the changes they have made are compatible, which parts are compatible, etc. So this requires one-to-one communication, typically for merging conflicts if done by two different developers. So imagine if you now have a very large-scale open source project having thousands of developers, having one-on-one communication pairwise on every single aspect of conflict that might arise is extremely prohibitive in terms of cost. So Git came up with a clean way of handling conflicts, which was like a huge leap forward compared to the existing code repository systems back in the day. And one of the ways at which it made this aspect of merging much easier is by having separation between what what happens locally versus what happens remote, and even within what happens locally, how do you think about changes that you do without having to worry about overwriting changes and then losing track of which changes correspond to what kind of development. So let's break it down. First and foremost, the notion of a remote code repository is something that I think is well understood by all of us because we've ended up using one such system in the last few years anyway. So GitHub is a good example, Bitbucket, GitLab, etc. It's basically a remote server which becomes the location for all the commits of a particular code base. And it's hosted by some entity or a server or a owner, and a lot of people have access to it through the public internet. So that's the concept of a remote server. You could have a remote code repository system within an organization as well, by the way, which is not facing the public internet, but it's on the local company LAN, right? So the company LAN allows you to access it as though it's a URI that's accessible to you. Whereas in local, what happens is that it's a location of all the commits that happen on that code base on a particular developer's machine, right? The code base could have multiple branches, right? So I'm not ruling out the fact that you might be working on 5 different branches at the same time. Doesn't matter. All those 5 branches are there on your local machine, and it allows you to work on each of those branch based on well-known commands, well-known semantics. We'll talk about those commands in a bit. The local itself comprises of 3 areas: the working tree, the staging area, and the local repo. Local repo, as you can imagine, is the storage area, which is basically where the code base is actually stored itself. The staging area is basically where the set of artifacts that you've changed or set of parts of the code that you've changed and you're planning to commit, but you've not committed yet. All of that uncommitted changes reside in what's called as the staging area. Think of it as a temporary area. Until you commit, it remains there. And the moment you make a commit from a staging area, obviously the commit is for a specific branch of the code base. Then there is a working tree that gets created, which is basically a snapshot of the branch, which comprises of the artifacts stored in one location for that particular single commit to be holistically complete. So in a sense, if you, let's say, operate on a branch, the overall code base has 5 branches, and you make, let's say, 10 commits in the course of a day, then you can expect to see about 10 different working trees based on for each such commit there is a tree. You might be planning a 11th such commit which has not yet been committed yet. So that 11th commit work, right? Basically, the set of unplanned, unsaved work that's there will be part of the staging area. The local repo in turn will have all 5 branches, but also will have this one branch where 10 commits have happened. Note that none of the work that's corresponding to those 10 changes or 10 commits have necessarily been sent to the remote yet, right? If you don't issue specific commands, it won't happen automatically. Local will be the place where it keeps getting buffered. Like, think of it that way. It keeps getting buffered there. So that's the notion of a local versus a remote. So let's say that you go through a typical Git based project development exercise. One of the first things you do is what's called as a checkout. A checkout happens by querying the remote server for a code base, right? And then that checkout will make uh, a copy of the directories and the files of that particular code base into your working tree, right? Because it constitutes a very clearly uh, checkpointed commit version that you're checking out. Let's say you're making changes now, and then once the changes are made, you've got to add those files that you've changed by using a command called as git add, and then that transfers these changes that you've made on the modified files into the staging area. After which, when you perform the command called as git commit, then it basically allows you to add a message so that you can verbally understand what is happening, and then those changes are committed to the local repository. Finally, these uh, performing git push is basically the command which pushes all the changes of your local branch to the remote back again, is then attempted from the local repo to the remote repository using git push. A pull request, on the other hand, is when the branch in the remote is merged, or you're looking to merge it with the main branch in remote, right? So when that kind of an exercise needs to happen, you issue a pull request, and then the pull request is sent to the owner of the main branch, who then approves or declines. And if he approves, the branch in the remote where you've made all the changes or you've pushed all the changes, that change or those sets of changes are then applied on the main once the pull request is approved. If the pull request is declined, then obviously no changes are propagated onto the main branch. Okay, so the common commands, we saw a couple of them now, but let's go through in sequence. When you first set up a repo, you do what's called as a git init, and then you work on the repo. Many a times we work on existing code repositories. The code repositories already exist in, let's say, a place like GitHub, which is a remote repo. So what you then do is you make a clone of that remote repo onto your local machine. So you execute git clone and give the URL. When we go through the examples, you'll see the working version of this. And then the clone actually creates a clone of that particular repo. Now, the clone means that you're getting an exact copy of what's there in the remote repo, but the remote repo might continue to see further changes. And the clone will not continue to keep in cloned, meaning that the clone operation is a one-time operation, right? At the time of executing the operation is when the copy happens. So keep that in mind. One of the useful commands I found, needing almost all the time is to use something called as git status. The status basically shows the set of changes which have not been committed yet, right? Changes that you have made to the local files. Now, if you don't add a particular changed file as part of the current commit that you're planning, it wouldn't show up as something that would get tracked by Git. Git actually, helpfully demarcates, files which are new, files which have been modified, files which are being tracked for commit. And so you will get a message, obviously, that says, hey, these sets of files are not being accounted for. So do you want to add it or do you want to ignore it? So that's useful, but keep in mind that git add is the definitive command that you want to use whenever you make a change and you want that change to be materialized or made permanent. Git commit, like we spoke about briefly, is the act of putting all those changes together with a useful, helpful message that you can later on refer to back again, and the commit creates the commit ID. Git push sends that all this commits to the remote branch, rather to the remote repo from your local repo. Usually Git push is for a particular branch. So what you do is you finish all the activity on your branch in local. You're ready, you're done for the day. You make it available to remote by doing a Git push. The reverse is also true. Like, let's say your colleague has worked on something uh, all night, and then you've come in fresh in the morning, and you want to continue from where you left off. So you can do a Git pull and get all the latest changes that have happened on that branch from remote to local. And then if you want to understand what those changes are, you can just take a look at the log by issuing git log. Okay, so let's talk about branching and merging, which is one of the key aspects of how you can get the best out of Git. So when you actually want to create a new branch from an existing code base, you effectively say git branch and give the name of the branch. Or if a branch already exists and you want to work on that particular branch, by default you would be when you clone, you get the entire set of branches, but you start off usually with the head. The head is usually the master branch, and then if you want to work on a specific branch, you can say git checkout and give the name of the branch. A checkout is like a what happens in a shopping cart, or a shopping mart, where you have a shopping cart and you feel that you're ready for doing the final act of purchase. So at that time you check out. Something similar happens here as well. So you're ready to start operating on a specific branch, and the set of changes for that branch are already done and committed. So you check out that branch and you start working on that. Merge, like I said, is merging changes between branches. Okay, so branches are a critical way to isolate changes that are necessary for various reasons. So one of the reasons why you might be working on a change in your machine learning project is you want to improve the model, which means you want to change the algorithm, you want to change um, the way the hyperparameters are, etc. So that's one angle. The second angle is you might be getting feedback that the model is performing poorly under certain conditions. So you're creating a version of the model which is meant to be good at working well in those conditions. So therefore you're creating an ensemble of models as an example. So in which case every model in that ensemble can be a different branch, so to speak. Or the other example would be you start to work on various pipeline improvements because the data quality has changed, and therefore you need to always maintain a champion challenger version. As you work through the iterations of the models, you want the previous iteration to be obviously continuing in production, but the newer iterations you want to experiment first and then take a call on whether you want to make that the champion model, right? So for those reasons as well, branches are a critical way in which you organize code, especially for machine learning as well. So one of the best, and simple rules of thumb is that if you're working on any change which is material, please work on a brand new branch, right? So call it whatever you want. Typically, if it's a feature, then you want to give it a name which has feature as a prefix. Or if it's a bug, then you can use a prefix like hotfix or bug, etc. But if you create a brand new branch, it makes it easy for you to work isolatedly and do your changes in a way that the impact is contained. And then once you're ready to promote to production, at that point you can do a reverse merge back into the main or issue a pull request. So to continue with the best practices, short-lived branches are branches that can be deleted after they've served a particular uh, you know purpose. So the purpose can be, for instance, a bug fix or implementing a very specific feature. So in which case you create a branch, work on that particular bug fix or a feature, test it out, prove it works, and then you push it back to the remote repo, and then issue a pull request to merge it back to the main branch, and the pull request gets approved, Once it's approved, you can go ahead and delete this bug fix branch. You don't need that anymore. So what this allows you to do is to merge frequently, right? Because you're operating on small things at a time, and each of the small things operate on a isolated individual branch, and then it forces you to merge into the main, and that act of merging frequently helps avoid a lot of the conflicts typically arising from asynchronous software development. Long-lived branches, on the other hand, also make sense for specific scenarios. These are when you've got versions of the code running in production, but they are no longer the latest versions of the code, right? Like for instance, let's say you've created a machine learning model for predicting uh, a particular outcome. Let's say, for instance, whether a person would buy a ticket or not, or buy a particular item or not. But as the uh, code has evolved, you have now created a separate recommendation engine, which has now become the state of the art. But the initial, predictor or purchase predictor continues to run live for certain workloads or certain users. So you don't want to change that, or you don't want to touch that yet, because the newer state of the art recommendation that you're building has not been proven at large scale. So what you then do is you can branch off this recommendation engine, the newer one, into its own branch, or you can make that the main branch, whereas the branch that's hosting the initial purchase predictor can be a long-lived branch which you continue to support, right? Which you continue to provide hot fixes or bug fixes until you're ready to completely retire it out. In those kinds of cases, long-lived branches also make sense. But typically, long-lived branches are not for non-production code. It's mainly meant for production code because there is an external dependency, right? For the code that for the set of artifacts that are part of that particular version. Okay, so let's you know uh, pause at this stage. We'll come back and take a look at what the best practice workflows are, and then the subsequent items around the rest of the GitHub actions, etc.